Hello students, these are our topic for discussion today. We will basically start with Coulomb's law. You all are familiar with Coulomb's law. So what was the law? If Q1 and Q2 charges are separated by distance, then the force between them is one by 4 pi epsilon naught Q1 times Q2 divided by R square. Here in this part, 1 by 4 pi epsilon naught is a constant quantity, which of value about 9 into 10 to the power 9 Newton meter square divided by Coulomb square. Here Coulomb is the unit of measure of charge. And epsilon naught is called permittivity of epsilon naught is called permittivity of free space. So now if the two charges are kept in a medium, then what will be the form of force? So in that case, we will replace epsilon naught by relative permittivity of that medium, that is epsilon. So here we need to define some another quantity called epsilon naught R. This is the relative permittivity. Epsilon naught is the relative permittivity of that medium. So epsilon naught R is ratio of permittivity of that medium and that of permittivity of free space. So we will put the value of epsilon naught as epsilon is equal to epsilon R into epsilon naught. What is epsilon naught? Epsilon is the permittivity of free space, and what is epsilon? The relative permittivity. So in that case, epsilon equals to epsilon naught R times epsilon naught. So epsilon is replaced by epsilon naught R times epsilon naught. So this is the general form of force of two charges, force between two charges kept in any medium. Now we will study Coulomb's law in vector form. What is the vector form of Coulomb's law? Then I define something F12. F12 represents what? It represents force on 1 due to 2. So here F12 represents force on Q1 due to Q2 charge. So in vector notation we need to define R as R12. Position vector of Q1 with respect to Q2. and F21 represents force on 2 due to 1. F21 represents force on Q2 due to the charge Q1. So in that case, we need to define position vector R21, that is position vector of charge Q2 with respect to charge 1. So in vector form, we need to rewrite the Coulomb's law as F21. We have to give the vector notation here. F21 will be 1 by 4 pi epsilon Q1 Q2 R21 whole square position vector of Q2 with respect to 1 whole square times R21 cap. R21 will represent a unit vector. Okay. So if you have not enough knowledge about vectors, then you can watch my lecture on scalars and vector. So now our next topic is definition of 1 coulomb charge. So in this equation, if we put R equal to 1 meter, Q1 equals Q2 equals 1 coulomb, then what will be the value of force? So 1 by 4 pi epsilon naught, the value of 1 by 4 pi epsilon naught is 9 into 10 to the power 9. Okay. Then Q1, Q2, 1 coulomb, and this is 1 square. This is basically, this part basically is 1. So we get 9 into 10 to the power 9 Newton. So now we need to define 1 coulomb. So how can we define 1 coulomb? So 1 coulomb is the charges that are placed at a distance of about 1 meter. Then they will repel each other with a force 9 into 10 to the power 9 Newton. So that charge will be 1 coulomb. So in this case, you can see 9 into 10 to the power 9 Newton. It's a very huge force. So in return, 1 coulomb charge is a very large amount of charge. So our next topic is electric field. So electric field is defined as the force on 1 coulomb charge due to some test charge Q1. Here Q1 is Q1 is source charge and Q2 is called as test charge. So we need to understand those quantities. Suppose this is Q1. To define electric field, we need to put Q2 as 1 coulomb, right? So this Q2 is test charge and this Q1 is source charge. So if we bring a test charge of about 1 coulomb to the vicinity of Q1 charge, then the force applied by Q1 charge on Q2 charge is the electric field, is called as electric field intensity. So we get a mathematical formula for electric field. So here you can see the value of Q2 is 1. So I will illustrate this concept in some another manner. Suppose this represents a king of kingdom and this area belongs to him. If inside this area some intruders enters, then the king will influence the intruders. So in our case, the king is Q1. If someone from the outside wants to enter this region, then the Q1 will act some force on that charge. So if the Q2 charge is 1 coulomb, then the force applied by Q1 on 1 coulomb charge is defined as the electric field. So this is plus 1 coulomb, right? So we have electric field 1 by 4 pi epsilon Q1 divided by R square. This is the distance between Q1 and 1 coulomb charge. So now what is the charge of a proton and the charge of an electron? As we all know that proton is positively charged and the electron is negatively charged. So our next topic is lines of force. So what is basically lines of force? So lines of force basically denotes the line of influence or the lines of electric field. Suppose the source charge is plus Q. Then what is the definition of electric field? The definition of electric field was the force created by plus Q charge on a by source charge on a plus 1 coulomb amount of charge. That is the definition of electric field. So if we imagine a plus 1 coulomb charge here, then what will happen? Plus q charge will repel plus 1 coulomb charge. So the direction of electric field or the lines of force is in this direction, along radially outward. So now if we consider a negative charge, then what will happen? So if we consider a negative charge, then what will be the direction of electric field? So we need to understand that plus q charge will attract plus 1 coulomb charge. That means the direction of electric field in this case is radially inward. Now we will draw lines of force for a plus q and minus q system, just like for a proton and electron system. So the lines of force comes from positive charge and enters to negative charge region. The direction of lines of force for a positive charge is radially outward, and for the negative charge is radially inward. So in this case, this arrow represents both. For positive charge it is radially outward, and for negative charge it is radially inward. This is basically a dipole. We will discuss about dipole and dipole moment in our next lecture. Thank you.